Okay, so in this video, we're going to go through some Python libraries for visualization, and mainly using Matplotlib, Seaborn, and a little bit on Altair. To do this, we're going to use the palmerpenguins dataset. That's a easy one to start with. And to load in the data, normally we could put into a content folder and upload from our desktop. Here, I'm not going to use this option. In fact, what I'm going to do is just load in the palmerpenguins through a pip install, and that's a package available and that you can access here using Google Colab or any Jupyter notebook. The data set, just to draw your attention to where the data set is from, it's Gorman, Williams, and Fraser, and they did some scientific research on Antarctica, and they looked at three islands, Dream, Torkelson, and Biscoe Island, and they traced three different species of penguin. The easy one to see here is the chin strap, and then I think the other one here, which is common to all three islands, is Adelie. And then Gentoo, which is a physically bigger penguin but a smaller bill. And some of the features that are related in the dataset are the bill length and the bill depth. And also there was information about the flipper length in millimeters, and then also the weight. And I'm going to load in here pandas for data transformation, and some other Python libraries for visualization, some Matplotlib, Seaborn, Plotly, but I don't use Plotly, Altair, and we're making available the palmerpenguins from the pip install. Okay, so we're going to create an object from penguins, and the data set we're going to refer to here as penguins. And then to get some sense of the dimensions of the data, I'll use a few pandas commands just to check that we have 344 columns, 344 rows and 8 columns. And then if there's any missing data, so there's 344 non-nulls in terms of species and on the islands. But then there seems to be two measurements missing. We have 342 non-nulls with bill lengths. So it means two bill lengths in millimeters weren't recorded. Likewise here for bill depth. The flipper, also two missing. Body mass, two missing. The sex, 11 missing. And then year, all recorded for year. To check which values are missing, we sum the NA. So if the value is a null, otherwise, in other words, we don't have a number recorded as an entry, we can sum up the missing lists from the penguins data set. Okay, and we can see that there's 11 penguins we haven't recorded the sex for, but when the record was made, we know exactly when, and otherwise just two missing. We know the species in each instance and also the island in each instance. And if we wanted just to make sure from again, we could just load into view. So if I hover I can create an outline here of what's in our data sets. If I go penguins.h head, open bracket, close bracket, we get a sort of an overview of what's in our data set. And you can see the species, island, bill length, bill depth in millimeters, flipper length, body mass in grams, sex, and year. And we can manipulate a little bit more. If I just say penguins, I get the full data set, but some missing values here. And if we wanted to manipulate more, we have this magic wand here that allows us to do a little bit more, take a deeper look here at our data set. And as we go through, we might find that there are a few missing values, especially in terms of sex. So if we come down here, by and by, we probably would find there's a missing value, another missing value, and so on. But each year is recorded, right? So that's handy. And I'll go back in and just load it up again so we get a full visual. And then we come down, and if we wanted to see which islands, then unique values for islands in the island column. There's Torgenson, there's Bisco, and Dream. And likewise for sex of the penguins, we've recorded male, female, and there was 11 missing records. For a pivot table, we could just do a count for each of the observations. And we notice here we've 152, 68, 124. And if you add the 3 up, we had the full record. We should get to 344 rows, right? But there was some missing values for sex. If we come down here, you can see there was a few Adelie we didn't record and a few Gentoo, but we seem to have managed to record all the sex of the chinstrap. Again, using pivot tables, we could group by sex and species and break down the mean flipper length. So when we take the compendium of data that was recorded in the penguins dataset and extract out the mean for Adelie Gentoo and break it down by female as an initial branch and categorizing the dataset, we notice that the females on average are smaller in terms of flipper length relative to the males. Okay, so the Adelie, chinstrap, Gentoo, always bigger. The females here are always smaller. And again, we could do something similar if I took the body mass here, Control C, and go back in and put in the mass, the body mass in grams, and take the mean. Typically, the males are bigger than the females. So the chinstrap male is bigger than the female. The Adelie male is bigger than the female, and so on. The Gentoo seems to be quite substantially bigger than the other 2 penguins. And if they're smaller in terms of dimensions, we might observe that in terms of the beak, in terms of the bill, right? So we might notice, although the Gentoo is bigger in terms of grams and in flipper size, he or she can be smaller in terms of the dimensions of the bill. Okay, so that's something that emerges as we go through. Now, objective here is really to perform visualization. And so these are just really openers that the pandas library is really just to break apart our data and take a look, but to get quick visuals and observe directly the breakdown along the different categories, we could use Matplotlib and combine it with pandas commands and generate a pie chart. So we see the relative number of male penguins to female penguins. It's fairly even, Stephen, marginally more males than females. If we look here at our code snippet, you can see here we have the number of decimal places. We go 2. We're counting the number of penguins, so we count the sex value in each of the categories for the sex, male or female, and then we break apart in terms of a visualization, identifying the males and the females. Likewise, we could run the same code again, but change just very basically, instead of the sex, we could put in here species, and we can see here that more Adderley in our sample, right, in our data set than Gen 2, and more Gen 2 than chinstrap overall. Adderley were on all 3 islands, Gen 2 just on one, and chinstrap just on another. Okay. And then in terms of the islands, if we substituted out here species and put in island, then we can see that most penguin, the biggest proportion of penguins we saw in Biscoe, then Dream, and then Turgenson. Okay, so we want to do some further visualizations. We're going to use Seaborn, Matplotlib, and we can set out the dimensions here as a sort of a template. And if we don't want warnings appearing or notices, we can ignore. And then a very useful tool in mapping out the relationship between continuous variables or scatter plots. And typically scatter plots are useful for visualizing the extent to which there's correlation between 2 variables. We can discern if there's a pattern or some kind of clustering or concentration, and the degree to which values are dispersed. And then we might also try to note, is it a positive relationship, a negative, or is one variable independent of the other? A very basic diagram here, or graph here, that we could use is the scatter graph. And what we've put on the x-axis is the bill length, and on the y-axis, the body mass. Okay, so on the x-axis, the bill length, and the y-axis, the body mass. And we then put in titles. So title and labels, and then show. Now, it would be useful if we could break this apart by category, so maybe by sex, or maybe by species, or maybe by island. So in the next snippet of code that we use here, we use Seaborn. And on the x-axis, we are going to use the bill depth, and on the y-axis, bill length. So we've moved a little bit away from mass, and we're getting here a legend that identifies which species. And we also have a different color for each of the species. So this is quite a nice piece of code. It's very short, relatively speaking, very concise, but it does a lot. And we can generate it using the Seaborn library, a scatter plot with X on the x-axis, the bill depth, and the y-axis, the bill length. The data set is penguins, and we can color code it so that the U captures the species. And then the size of the dots, 10, color black. And sorry, the bill depth versus bill length. So if we change that to be smaller, it'll change the title here. Okay, so let's go back to 5 and observe directly what that does. And you can see it makes it smaller, or we could make it 10. So here in the title, we adjust that and we can make the size a bit bigger. Okay, now we could adjust, switch around here the x-axis for the y-axis. That's done simply enough. And you can see if I just come down to the cell below here, if I change the X to the bill length and the Y to the bill depth, then I'm switching around the axes. And you can see we get the bill length here on the horizontal axis and the bill depth on the vertical axis. Looking at this, if we didn't color code, you might be tempted to put, if you're saying what's the correlation between the bill depth and the bill length, you might say there's a negative relationship to through all the dots if you combined all the data points together. But it's more likely that when you break it down by species, there's a positive correlation. And again, one of the very nice features here with Seaborn is we can do a reg plot where we introduce a trend line into our data. So the Seaborn reg plot is employed to add trend lines, and we can do that by specifying the parameter by code and then add the trend line. So we can do a global trend line here, and then we can do a trend line specifically for the Gen 2, for the Adderley, for the Gen 2, and for the chinstrap. And we can see here each of the colors denoting a specific species and the trend line to boot, right? And on the whole here, we can observe that there's a positive relationship between bill length and bill depth, which would be sort of intuitive. And I'll take a look at the data, the code snippet here. We import in Seaborn, Matplotlib. We set out the scatter plot as before, and we break it down by species. And then we add a trend line for the entire population, and then we add a separate trend line for each of the individual species. Same as before, can increase, if we want to run that again, and increase the title size, let's say to 15. Mightn't be terribly aesthetic if we do that, but we'll see in a moment that tends to increase. If we put it back to 10 and run as it was, then the title will get a bit smaller. Okay, so we have the code here and then the plot underneath. Okay, now histograms are useful for getting a sense of the distribution of a data set. And here we're going to use the Seaborn library again. And we're going to just do a basic count where just breaking apart, if you like, the bill length and how it straddles the population. So we count the number of observation in each bandwidth, and we can determine the bandwidth here by changing, we can augment or increase. Now the size here denotes the title and the color, but we can also change, we'll see in a moment how we can change the bandwidth here in a moment, so that we have different bands, maybe more detailed bands or less detailed bands. Okay, so that's useful for getting sort of the distribution of the bill length with the penguin data set. If we come down and just change to Y, you can see the effect from changing from X to Y. We flip, if you like, the chart on its side. So it's still the same basic representation as what we've got here. We've just flipped it over on its side. And then if we want to put in the bin width, right, and change that, let's say from 10 down to 5, and run that again, you can see we get a much more detailed set of bins. And if we can put it down to 2, try that again, I might get some gaps appearing, right? So it's not continuous, a bit ratchety. So we could increase the bin width to maybe 5 and run again. So again, the histogram here allows us to plot out the distribution of, in this instance, we're using the flipper length and we're counting the number of observations within the bands. So number of penguins that satisfy those particular bands. Again, you can change a little bit the bandwidth or the bin width and, create larger bins. And again, that's kind of can be useful for providing us with some sense of the spread of the variable. Again, the flipper length, we can change that to something maybe more strongly visible, so black. And run again, and we change the label color. And as always, we can increase the label size or the title size. Okay, so flipper length. Again, we could do histogram, but manipulating the detail here so that we identify or break apart the species. Okay, and it's fairly clear if we look at the flipper length that Gen2 is bigger. Then the chin strap seems to be more in the middle, and Adelaide has shorter flipper length, although there is some overlap. And if we wanted to, I suppose we could change before we were using the grams or mass. So if we wanted to observe that distribution, Control V, body mass grams, run this command again, and we get the distribution of the weight in grams of each of the species. And again, the Gen2 is bigger than the chin strap, and Adelaide. Adelaide tends to be smaller, but there's a bit of overlap here. And again, we can form a view about the size of. Now, it wouldn't be flipper length. Probably have to change that also to be consistent. But in terms of the body mass, and run that again. And again, that's from the Seaborn library. We're getting the body mass, a histogram plot, manipulating the U parameter to visualize histograms by category. Bar plots are a specific type of visualization that's available in Seaborn, and they're useful for creating a measure, a bit like bar charts, but the bar plot might represent the mean value, for instance, and then we can identify some kind of a measure of error or uncertainty in the visualization. Bar plots, also known as bar chart, is a visual representation of the categorical data using rectangular bars. So to give a sense of that, what we have here is the average flipper length, and Gen2's biggest, then chin strap, then Adelaide. Adelaide seems to be the smaller of the species, and then the uncertainty measure is given by this black stroke in the bins. Okay, so again, we could do as before. We could look at specifically at the body mass, and then maybe write that in here as well, the body mass in grams. Run the same command again, and we can see here Gen2 is quite a bit bigger compared to chin strap, and then chin strap seems to be ever so slightly bigger than the Adelaide. More of evidence of a distribution, or the confidence interval is wider. So more of a sense of spread here, right? So we're getting mean values for each of them, and then we can line up and compare against the other. And again, this is coming from Seaborn. We could break that apart. So again, the same as here, right? We could take the same command that we have here, but we could break it apart by sex. So if I go back and say U is equal to sex, and put in inverted commas, and run this again. Okay, and if I came up here and again just change ever so slightly the command U equal to, let me put in the sex, we could break apart our bar plot. So it takes on board, so it should be equal to here, and run. And again, you see we've broken down the distribution, the means. So not so much distribution, but we're looking at each of the species, and we can break it down by sex. And we're taking the average value for, in this case, it is the body mass, right? For the three species. But again, in each instance, we can see that the Gen 2 tends to be bigger for males, and that blue bigger than the Adelaide and bigger than the chin strap. And the chin strap female seems to be slightly bigger than the female Adelaide. And the female Gen 2 is the biggest of all in terms of body mass. Again, the x-axis represents the different penguin species, and the y-axis the average. And we have here flipper length, but would have been the body mass. And okay, so we could change this to maybe body mass. And we can redocument, right, our text here so that it reflects what's in the graph. Okay, and then coming down, we've executed this before, and box plots tend to give us a spread of the distribution, so breaks apart the interquartile range, and typically we get the interquartile range. So this value here, let's just take a look. So we're looking at each of the species. We're looking at the flipper length in millimeters. The Adelaide median value is less than the median value for the chin strap, and the Gen 2 has the highest median value of all three species in terms of the flipper length for the three species. Then there's the interquartile range, so the 25 percentile to the 75 percentile, same across the board, right, in terms of structure. And then we have the outliers, and typically the maximum and minimum here represent going 1.25 times interquartile range. And then this is the final value before reaching the outlier. So we're exceeding 1.25 times the interquartile range. And then we touch the outliers. Okay, now we can break that just if we put in here change ever so slightly, or augment our code ever so slightly. So if we put in U again equal to sex, we can break apart the graph. So we have male and female side by side. Okay, and so that's sort of a powerful tool to make the comparisons. Okay, a facet plot, you can use a facet grid to grid graph different subsets of the data set. And again, here, very relatively straightforward syntax for Seaborn. We do SNS to call in the Seaborn library, then facet grid, and we're producing a histogram for each of the different islands, right? And then on the row, we're looking at the male and female, right? So we have sex female, sex female, sex female, and above in the top row we have sex male, sex male, sex male, and we're breaking it down into columns. we're breaking it down by Turkinson, Bisco, and Dream. Okay, now again, just to make the comparisons, it might be useful to have this two-dimensional visualization because it allows us to get a sense of what's going on each island, right? And again, we could do something similar here, but apply a disk plot. And again, something quite similar in terms of the pattern distribution. And then the pair plots, probably the one here that provides us with, very simple syntax, SNS pair plot, and we're going to break apart by species, and the height is 2. So if we change the height here to 5 and run that again, and note that the pair plot function creates a grid of scatter plots and histograms where each variable is plotted against each other variable. And you can see we've increased the dimension of the graphs, and size here is a little bit too big for us to get a kind of overall. Now we can zoom out. That might be useful. Let's run it again and just put in a value on the height here of 2. So we revert back to the original. The reason why it takes so long is that there's so many dots that have to be generated, and I'm sure it involves quite a bit of processing. But the pair plot allows us to pull in the data frame, and then we can specify what we could change this to islands, but the category, if we want to break it down by species, we set the U equal to species, and then the argument uses species column to color code the data points based on different species of penguins. If we pull out here, we can see a little bit on the horizontal axis here, bill length, bill depth, flipper length, body mass. So we're generating, and the year. So we're generating and breaking apart, color coding the dots based on the species. And again, it's fairly clear that if we take the body mass, for instance, here, the Gen 2 species is the biggest. And when we compare the flipper length to the body mass, we can see here that consistently there's a pattern here, fairly coherent pattern, that the biggest of the 3 species is the Gen 2, both by flipper length and body mass. However, when we look at the bill depth and body mass, Gen 2 has the biggest body mass, but the bill depth tends to be smaller than the other 2 penguins, right? So while the Gen 2 is bigger, some of the dimensions can be small, especially relating to the bill depth. Bill length, the Gen 2 has a long bill, or the bill is reasonably long, but the chin strap possibly typically bigger, and the adelaide typically smaller, and the Gen 2 is middle of the range. But in terms of the bill depth, Gen 2 is smallest, but appear to be typically smaller than the other 2 species. Okay, and we can break apart by years. Now we only have 3 years, 2007, 8, and 9. And it's color coded. And then here we have each species assigned a different color, making it easy to distinguish data points from different species. And the height 2 argument sets the height of each individual subplot in the pair plot, as we saw before. We could use on the diagonal here, we could generate a histogram. The default is this type of distribution, but if we preferred a histogram and we broke it apart by species, you can see it's a small change, but a useful change if we wanted to just visualize the pattern in terms of how the different variables relate to each other. We can provide also a heat map, which takes a correlation matrix, and that is, we estimate the correlation between the variables. If it's a negative, means the values move in opposite directions. So the build depth and the build length for the entire group was negative, but when we break it down, it's positive by species. So we've taken the population here, the sample, as the entire group, and we saw before it's negative for the group, but positive for when you break it down by the individual species. And we see negative and positive values here. And on the diagonal, as expected, the correlation between body mass and body mass is 1, between year and year is 1, between flipper length and flipper length 1, and so on. Okay, and again, for pre-modeling and pre-processing, correlation matrix, very useful to establish at a very basic level the interrelationships between variables. But here we're just setting out the heat map as an interesting visualization. Again, very simple syntax and a simple command. And then for a bar chart here, just to run, and we're doing Seaborn and a count plot. So this is not getting the average, this is counting the number of each category. And again, we can do the look at the distribution of the variables with the box plot. And a very detailed visualization would, okay, so if we're comparing, let's say, the bill length and the body mass, but wanting to break apart by species, and then using the size of the dot to denote the different islands, and then break it by male and female. So the small dots are Dream, the big dots are Turgensen. And then we color code for species, and male is a circle, female is an X, and it would appear 50-50. And the females tend to be smaller than their male counterparts. Female X's here are smaller than their male counterparts, and the female X's here are smaller than the dots, which are the male counterparts. So again, a very nice way of taking on board, capturing in a multifaceted way the different categorical variables for the penguin dataset. And then the snippet of code here I'm going to use is from Altair. And when we run it, we get a sort of interactive graph. And doing something similar now, it's we can save or we can edit further, but it's a nice way to play around with the data and just go a little bit deeper in on what's there. And we could take a look at a few data points at a time, right? So that's an interesting way to manipulate the data in a 3D, in an interactive fashion using Altair.